this video, the theorems in prime modulus in number theory will be discussed. So the first theorem we are going to see is the concurrence f of x concurrent to 0 mod p of degree n has at most n solutions. So in this theorem, the proof is by the induction on n the degree of f of x concurrent to 0 mod p. The degree of a polynomial is different from the degree of a polynomial concurrent to 0 mod p. If n equal to 0, then f of x equal to a naught and a naught is not equal to 0 mod p. Therefore, f of x concurrent to 0 mod p has no solution. If n is equal to 1, then f of x will be a naught plus a1x mod p. So which implies a naught plus a1x concurrent to 0 mod p if and only if a1x concurrent to minus a naught mod p holds. Since p does not divides a1 and the GCD of a1 and p is 1, a1x concurrent to minus a naught mod p has a unique solution, which implies f of x concurrent to 0 mod p has a solution. So we have proved that this theorem is true for the case n equal to 0 and 1. So assume that every concurrence of degree less than n, that is at most n minus 1, has at most n minus 1 solutions. Let f of x concurrent to 0 mod p be of degree n, where f of x is nothing but a naught plus a1x plus etc. an x power n, and p does not divide an. Since the degree is n, p must not divide an. So our aim is f of x concurrent to 0 mod p has at most n solution. That's we have to prove. So we are going to assume the contrary. That is, f of x concurrent to 0 mod p has at least n plus 1 solutions. So we are going to denote the n plus 1 solutions as u1, u2, un etc. un plus 1. With the condition that ui not concurrent to uj mod p for I not equal to j. We are going to consider another polynomial g of x as f of x minus an into x minus u1, x minus u2, etc. x minus un mod p. Then g of x is a polynomial of degree at most n minus 1. So our case first one is, we are going to consider g of x concurrent to 0 mod p has degree at most n minus 1. So then by the inductive hypothesis, g of x concurrent to 0 mod p has at most n minus 1 solutions. So which implies g of ui concurrent to f of ui mod p. So f of ui is already 0 since ui is a solution for f of x concurrent to 0 mod p. Therefore, g of x concurrent to 0 mod p has at least n solution, which is a contradiction to this. G of x concurrent to 0 mod p has at most n minus 1 solutions. So another case we are going to consider as g of x concurrent to 0 mod p has no degree. So every coefficient of g of x is divisible by p, which implies every integer is a solution of g of x concurrent to 0 mod p. So in particular, un plus 1 is a solution of this. So which implies g of un plus 1 concurrent to 0 mod p. So from the equation number 1, we are getting this is E concurrent to 0 mod p. Since f of un plus 1 concurrent to 0 mod p, we are getting this. So which implies p divides this value. Since p does not divide an, p should divide any one of this un plus 1 minus ui. So which implies un plus 1 concurrent to ui mod p, which is a contradiction to the fact that ui does not concurrent to uj mod p for I not equal to j. So in both the cases, we arrived at the conclusion that our assumption is wrong. Hence, f of x concurrent to 0 mod p has at most n solution, where f of x concurrent to 0 mod p is a polynomial of degree n at most n. So in this corollary, we are going to see that if bn x power n plus bn minus 1 x power n minus 1 plus etc. b not concurrent to 0 mod p has more than n solutions, then all the coefficients bj are divisible by p. So this corollary is going to prove by contradiction. So we are going to assume, suppose p does not divide some bi, which implies b naught plus b1x plus etc. this bn x power n concurrent to 0 mod p has degree at most n. So which implies this will be concurrent to 0 mod p has at most n solution by previous theorem. So which is a contradiction to our assumption, because we have assumed that this has at more than n solution. Therefore, all the coefficients bj must be divisible by p. So the next theorem is the concurrence f of x concurrent to 0 mod p of degree n with leading coefficient an equal to 1 has n solution if and only if f of x is a factor of x power p minus x modulo p. That is, if and only if xp minus x equal to f of x into q of x plus p into s of x, where q of x and x of x have integral coefficients. Q of x has degree p minus n and leading coefficient 1, and where either x of x is a polynomial of degree less than n or s of x is a 0. So first we are going to assume that f of x concurrent to 0 mod p has n solutions. Then this n must be less than or equal to p. So dividing x power p minus x by f of x, we get x power p minus x equal to f of x into q of x plus r of x, where q of x is the quotient and r of x is the remainder, and the remainder either will be 0 or is a polynomial degree less than n, that is at most degree n minus 1. So by Fermat's theorem, we know that a power p concurrent to a mod p. So here we are writing that x power p minus x concurrent to 0 mod p for every x. So which implies f of x q into q of x plus r of x concurrent to 0 mod p for every x. So which implies f of x into q of x concurrent to minus r of x mod p for every x. So which holds f of x concurrent to 0 mod p if and only if f of x into q of x concurrent to 0 mod p if and only if minus r of x concurrent to 0 mod p if and only if r of x concurrent to 0 mod p has at least n solution. By the previous corollary, r of x is divisible by p, that is p divides r of x, which implies r of x equal to some p into s of x. So from the equation number 1, we are getting x power p minus x equal to f of x into q of x. In the place of r of x, we are writing p into s of x, where either s of x equal to 0 or it is a polynomial of degree less than n. Since x power p minus x has degree p and the leading coefficient 1, and f of s has degree n and leading coefficient 1, it follows that q of x has degree p minus 1, p minus n and leading coefficient 1. So conversely, assuming that x power p minus x equal to f of x into q of x plus p into s of x, where q of x and s of x have integral coefficient and q of x has degree p minus n and leading coefficient 1, and where either s of x equal to 0 or s of x is a polynomial of degree less than n. Here also we are going to use the Fermat's theorem, x power p minus x concurrent to 0 mod p, which implies x power p minus x concurrent to 0 mod p has p solutions. So finally we are getting the f of x into q of x concurrent to 0 mod p has p solutions. Since x power p minus x has leading term x power p, the leading term of f of x is x power n. By the hypothesis, it follows that the leading term of q of x is x power p minus n. So we are getting f of x concurrent to 0 mod p and q of x concurrent to 0 mod p have at most n solution and p minus n solution respectively. So but every one of the p solution of f of x into q of x concurrent to 0 mod p is a solution of at least one of the concurrents f of x concurrent to 0 mod p and q of x concurrent to 0 mod p. So hence we got f of x concurrent to 0 mod p and q of x concurrent to 0 mod p have exactly n solution and p minus n solution respectively. Hence we have proved both the necessary and sufficient part of this theorem. So in this corollary, we are going to see that if d divides p minus 1, then x power d concurrent to 1 mod p has d solutions. So we are going to assume x power d minus 1 as f of x. then x power d minus 1 concurrent to 0 mod p becomes f of x concurrent to 0 mod p. So they have given d divides p minus 1, that is p minus 1 equal to d into some integer e. Since y minus 1 into 1 plus y into etc. y power e minus 1 equal to y power e minus 1, I am going to take y as x power d. So we will get x power d minus 1 into 1 plus x power d plus etc. x power d into e minus 1. So we are getting x power d e minus 1, which is nothing but x power p minus 1. Since de is p minus 1. So we are going to multiply both sides by x. So we are getting x into x power d minus 1 and 1 plus x power d plus etc. x power d into e minus 1 equal to x power p minus x. So now x power p minus x is nothing but x power d minus 1 into q of x, where we are considering the remaining terms as q of x. So we are getting this as x power d minus 1 into q of x plus p s of x, where here s of x equal to 0. Therefore, the degree of q of x is de minus d plus 1. So de is p minus 1 minus d plus 1. So we are getting p minus d. So hence by the previous theorem, we are getting f of x equal to x power d minus 1 has exactly these solutions. So hence from the corollary, we conclude that if d divides p minus 1 and then x power d concurrent to 1 mod p has d solutions. Thank you.